In the last video, we related the ideal gas law to Newton's second law of motion, F equals ma. And here we're going to just spend a moment to use the ideal gas law to get the classic forms of the gas laws that you may have learned if you have had some prior experience in chemistry. And historically, the way the ideal gas law was developed was that particularly chemists had been noticing all sorts of relations between pressures and temperatures for different kinds of processes. And then eventually people were able to model all these empirical relations together into one unified statement. So let's go and take a look at an isochoric process. Now, all of these processes will have names that begin with iso, which means the same. I'll introduce an adiabatic process later. You may have seen this written as isovolumetric. In either case, it means the same volume. So this is a process where the volume will not change. So we can imagine, say, just having a gas in a vessel. We go ahead and put a little pressure gauge on here. We apply some heat to the vessel, like so. Maybe put a Bunsen burner there, something like that. And we know, just practically speaking, the pressure is going to go up. And so now we can analyze this through the ideal gas law. And I'm a big fan here of using scaling so that you don't have to remember a bunch of separate gas laws. So here we can write down PV equals nRT. And what we'll do is we'll put final subscripts on the things that change, final initial subscripts on the things that change, and don't subscript the things that don't change. So here I can write P final and T final. The volume doesn't change, so it doesn't get a subscript. Number of moles doesn't change, so it doesn't get a subscript. And I hope the ideal gas constant doesn't change, because that's not a constant. Now I can divide this side by P initial V, as long as I divide it by what it's equal to over here. So now what this gives me is the V's cancel, the N's and R's cancel, and I am left with P final is to P initial as T final is to T initial. And you may have seen this before. This is also known as Gay-Lussac's law. So historically, Gay-Lussac's law was one of the inputs into the ideal gas law, but here, since we've derived the ideal gas law from F equals ma, I'm just going through and recovering the processes. Now, one of the things that physicists like to draw to help visualize these processes are things called PV diagrams. This is where you draw two axes, pressure, volume. You just literally draw dots to mark the initial and the final. So here, and then you just draw whatever the path is that connects your initial to the final with an arrowhead to help guide the viewer to figure out which way you're going. So this is not a graph. It's just saying, hey, I started at this pressure, now I'm at that pressure. And the volume didn't change because the volume's a constant. Now, if you can draw these curves at all, then this means that the process is undergoing what's called the quasi-static process assumption. And what's at issue here is if you're to crank the heat up too quick, the temperature throughout the vessel would not be uniform, and you would not have a well-defined pressure for the entire vessel. So you wouldn't be able to meaningfully draw a dot to say, well, the pressure right now is this. You could maybe draw a dot at the beginning, a dot at the end, and then just write basically a giant WTF in the middle because you don't know how the two connect. So we're going to have to assume that all these processes go very slowly. In fact, if you can draw them, they're reversible, but it's good enough for us to just assume it's very slowly. Okay, let's take a look at another process. This one would be an isobaric process. So again, you look at it and say the same, iso means the same what? Bar, like as in barometric pressure? Yes. So this means that it is the same pressure. So P will be equal to a constant here. So here what I'm imagining is I've got my vessel, but now I've got, say, a piston that's free to slide, and this piston has some weight. So I can go ahead and heat up the substance, as an example here. And as I do, what will happen is the average thermal energy of the atoms will increase. That means they'll start pushing harder against this. And so it will move up. Move up to where? Well, as it moves up, the gas was doing work on this, and so the thermal energy had to drop back down. But of course, we're continuing to keep inputting heat into the system. So sorry, let me try that again. So the pressure here is going to stay the same. We did work, so heat is going in to do work to raise the piston. All right. So we can again do this by writing the ideal gas law, PV equals nRT. Put subscripts on the things that change. This will be V and T because this isn't insulated, so we can have heat transfers in and out. And then divide it by the same thing, but for the initial scenario. So again, we can go ahead and cancel out common factors. And we are left with V final over V initial equals T final over T initial. This is Charles' law. We can go ahead and draw a PV diagram for this. So here the volume got bigger, but the pressure stayed the same. So we can label my initial, my final, and there you go, like so. So the last of these I'm going to look at for the moment will be an isothermal process. And so again, you'll like I say isothermal, the same. And then you have to ask yourself, okay, the same what? In this case, what's going to be the same is the temperature. So here, T is equal to a constant. So here now I can imagine taking my piston, that's like so, and I sit this thing inside a giant water bath, and I make sure that there are ice cubes floating in the water bath in order to ensure that the temperature is 0 degrees. Then maybe I go ahead and push on the piston, let's say. I push on the piston, the volume of the cylinder will have decreased. So here again we can write start by writing the ideal gas law, say PV equals nRT. Put final subscripts on the things that change, no subscripts on the things that don't. So here, the N's, R's, and T's all cancel just to leave us a 1 over there. And so then I can multiply through by P initial, V initial to get P final, V final equals P initial, V initial, which is Boyle's law. So these three laws plus some others, when combined, people realized that the overarching statement of all of these was the ideal gas law. All right, so let's think about what a PV diagram would look like for this. So both the pressure and the volume are changing, but they're changing such that the temperature is a constant. So if I look here, say if the pressure doubled, the volume would have to drop in half. So you have to have some sort of an inverse relationship. So say for this process that I did here where we have a compression, that would look, say, something like this. The volume was bigger, got smaller. The shape of the curve here is going to be, the pressure will have to go through the reciprocal of the volume. Now, where exactly this curve is situated depends on the temperature. If we were maintaining the temperature lower, it would fall along a curve that looked something like that. So I'll just label this as a lower temperature. And again, this is pressure goes 1 over volume. The only difference is just the constant involved. And if it were a higher temperature, say here, it would look something like that. So these curves that goes 1 over V, they usually get called isotherms. So this is just a fancy way of saying something where the pressure goes as 1 over V in the diagram. Alrighty. So in the next video, we'll turn our attention to looking at some heat transfer processes. Catch you over there.